Hello, so now we're going to do AP number 10, and it says here no calculator is allowed for these problems. Okay, we're given a chart, T is in minutes and C of T is in ounces. And it says hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time T between 0 and 6 minutes is given by a differentiable function C where T is measured in minutes. Selected values of C of T measured in ounces are given in the table above. So please note that C of T tells us the number of ounces of coffee. It is not a rate of change. So part A begins with the following question. It says, use the data in the table to approximate the derivative of C at 3.5. Show the computations that lead to your answer and indicate units of measure. So to find the derivative, or to approximate the derivative, we don't know what the function is, but we could certainly get the slope of the secant line between the points that contain 3.5, and those are 3 and 4. So we evaluate C at 4, subtract C at 3, over 4 minus 3. And this is an approximation now for the derivative of C at 3.5, the slope of the secant line to the function between 3 and 4. So C of 4 is 12.8, C of 3 is 11.2, and 4 minus 3 is 1. So when we subtract, we get 1.6, but the units, because they do say indicate units, so it would be 1.6 ounces per minute. Okay, because this is a derivative. All right, let's move to part B. Okay, let's just put a box around that answer. Okay, so part B says, is there a time between 2 and 4 at which the derivative of C is 2? Justify your answer. Okay, now whenever we're asked about the existence of a derivative of a function, and we know that the function that's given is differentiable, we immediately go to the mean value theorem. And let's make sure we state the hypothesis. We're given that C's differentiable function from 0 to 6, which implies C is a continuous function from 0 to 6, in particular the interval from 2 to 4. So by the mean value theorem, there exists some x in the interval 2 to 4, so that the derivative of C at x is equal to C at 4 minus C at 2 over 4 minus 2. Substituting C of 4, which is 12.8, and C of 2, which is 8.8, and doing the math, we get that the derivative of C at x is 2. So the answer is yes, it is true. Really, this x is a t, because it's time, but it doesn't matter. I mean, according to the mean value theorem, we also call it a C, but C is a poor variable to use because C is used as the name of the function, so maybe we're better off calling it T. So there exists a T, time, in 2 to 4, so that the derivative of C at that time is C of 4 minus C of 2 over 4 minus 2. Okay, let's take a look at part C. Part C says, use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of that integral 1/6 of 0 to 6 of C of T dt. Okay, well, it turns out that if we're going to take 3 subintervals, we're going to divide 0 to 6 into 3 subintervals of equal width. So delta x equals b minus a over n, which is 6 minus 0 over 3, and that gives that the width of each subinterval is 2. So the subintervals are 0 to 2, 2 to 4, and 4 to 6. I think it's easy to see that those would be the subintervals. Let's just indicate them on the chart. So the midpoint would be these values: 5.3, 11.2, and 13.8. And delta x in each of these cases is 2 units apart. Remember, whatever RAM we use, left, right, or midpoint, that's always the y value in that respective subinterval. So let's compute it on the next page. So on the next page, if we use a midpoint RAM, we have 2 times the midpoint of the first subinterval, 2 times the midpoint of the second subinterval, and 2 times the midpoint of the third subinterval, which would represent the areas of the rectangles in that subinterval. So we get 2 times 5.3, 2 times 11.2, and 2 times 13.8. And let's just do the math. Okay, this gives, and this is without a calculator, so 5.3 times 2 is 10.6, that's good. This gives us 22.4, that's good. And this gives us 16, let's see, 13.8 times 2, I have to do this on the side. 16 carry the 1 is 7, and we get 27.6. And now let's just add them all up. So we're going to add 10.6 with 22.4 plus 27.6. Here we get 16, carry the 1. Here we get 7 and 2 is 9 and 1 is 10, carry the 1. And 2, 4, 6. So the answer is 60.6. Now the unit would be in ounces. Because remember, we are multiplying minutes we're multiplying minute by ounces, minute by ounces, minute by ounces. Oh, so actually, this is not the definite integral of a derivative. So I'm wrong here. This unit here, well, let me just get my eraser. Something strange is happening. Okay, so this unit here is ounces, minute, ounces and minute ounces. However, if we take this expression and they're asking us, what does this expression mean? So we're asked, what does the expression 1/6 from 0 to 6 of C of t dt mean? Okay, we haven't learned this yet, but this represents the average value of the function, of the function f. So the formula for that, which we will learn in class, is 1 over b minus a times the definite integral from a to b of f of x dx. So because this is in, actually the units for this integral would be, because we're multiplying the ounces by the minutes, this unit is ounces times minutes. However, 1 over 6 would represent, 1 is in terms of 1/6 minutes, and the minutes are on the bottom, 1 over 6 minutes. So if we multiply 1 over 6 minutes times ounces minutes, our answer is in ounces. So this expression would be 1/6 of 60.6, which would give us 10.1 ounces, and the 10.1 ounces of tea represents the average amount of tea that was poured in the time interval between 0 and 6 minutes, or the average amount of tea that was poured in the first 6 minutes. I'm sorry, I didn't realize it's coffee, not tea. So let's just correct that quickly. I can't believe I did that, but I guess it's okay. So let's just erase this and write coffee. Okay, so we have coffee. Oops, that's too thick. Let me just make it a tiny bit. Okay, coffee. Oh, now it's becoming too thick, but that should be coffee. All right, let me just try to correct this. Okay, now it looks better. Now let's take a look at part D. So part D says that the amount of coffee in the cup is modeled by this equation at time t. And we have to find out the rate at which the coffee is being poured into the mug at t equals 5. So that's really just asking us to get the derivative of b at 5. Now we could do this by hand. First we would differentiate this, and the derivative of this is just 0 minus 16 e to the negative 0.4t times negative 0.4. By the chain rule, we have to take the derivative of the exponent. And let's see what that simplifies to. That simplifies into positive 6.4 e to the negative 0.4t. So at 5, the derivative would be 6.4 e to the negative 0.4 times 5, which is just 6.4 e to the negative 1.0. And I guess that would be the answers, ounces per minute. And that, I believe, would complete this AP question. All right, that one wasn't too bad. It was just testing to see if we know what the derivative means and how to get it. But if it were a calculator question, we could very well put this in our calculator and it could get the derivative for us. Of course, the calculator would use the approximation for e and give us a decimal. And with that decimal, we would have to round it correct to 3 decimal places. But this was a non-calculator problem, so we'll just leave it just like this. I believe my arithmetic is correct. 16 times 0.4 gives you 24, and 2 is 6. Yeah, I think it's okay. All right, that takes care of this AP. Thanks very much for listening, and I'll see you soon. Bye.